Avarnitaki. You can try to share your screen. Hi.
Yeah, let me share my screen.
Okay.
Sorry, let's see here. Can you see it?
Can you move the cursor so that we can see? I mean, unless you don't need it. Ah, okay.
At this, the bottom thing. Oh God. Okay, how do I move the bottom thing?
No, just the cursor. That's like, does it work? Okay.
What's cursor? Sorry.
No, I mean, I was okay.
Oh,
it's just your arrow.
okay.
Like we see your arrow. Don't worry.
Okay,
don't worry.
great. Okay, let me go back now. Okay, great. Went back.
Okay.
Anyway, thank you very much for reminding me to give this talk. First of all, I need to apologize to the organizers because they actually did not invite me to give this talk. They invited me to give a talk on black hole superradiance
but
and
we are happy. We are
gravitational.
We are even
gravitational
happier.
waves.
We are even happier.
Yeah, gravitational waves can be used to probe black holes. Actually, astrophysical black holes can be used to probe axions and any ultralight boson. Well, I mean, you can ask me later about it if you want to hear. I'll briefly mention during the talk because such an effect already constrains axions. Now, the thing I'm actually going to talk about is a new observable that Ken and I, along with my student Amalia Madden, recently discovered that can be used to probe axion dark matter and other type of effects. So now, before I tell you exactly what this observable is, I will say that this is a dark matter search, and we know dark matter is there. We have many ideas about what dark matter can be. In fact, if one tries to put the ideas that we have for dark matter in an energy scale, it's some 80 orders of magnitude. Now, the thing is that many of these ideas, though, do not have a consistent cosmology or a very well thought out production mechanism. So this is where ideas like the weakly interactive massive particles are extremely popular. And as I will show today, axions, and of course, in this audience, maybe I don't have to, axions have a production mechanism, and that makes them extremely attractive as a dark matter candidate. The other thing is that axions also have interactions other than gravitation, so you can build experiments in the lab to look for them. Now, the king of all axions is the QCD axion, because it actually solves a puzzle of the standard model. Now, it was proposed back in the 80s to explain the smallness of the electric dipole moment. And as such, I want to point out that the QCD axion couples to the gluon, the strong interaction anomaly. And this is actually the coupling that will be central to my talk today. Now, the other great thing about the axion, the QCD axion in particular, is that it's a great experimental target. Its mass and its couplings are uniquely determined by the axion decay constant. And despite experimentalist theorists, I should say, best efforts to expand the QCD axion parameter space, this model-independent coupling, the axion of the coupling to the QCD axion is actually very hard to modify. The QCD axion, as I say, is king among all axions, not only because it has a very well-defined, it solves an existing theoretical puzzle, but it's a great experimental target because of the very nice one-dimensional parameter space. Now, when you go to bigger extension of the standard model, as was mentioned previously, axions become ubiquitous. And for example, if you take string theory, you can have, in fact, more than one cousin of the QCD axion. This happens because in string theory, there are three main ingredients. There are extra dimensions that you need to make the theory mathematically consistent. There are gauge fields that live in these extra dimensions. And there is topology. Basically, we need to compactify these extra dimensions to give rise to our four-dimensional world. Now, we can compactify them simply on a sphere or on a torus, or in fact, the way we can compactify these extra dimensions is only limited by people's imagination. Now, if you have gauge fields living in extra dimensions that have non-trivial topology, you find that these gauge fields in 4 dimensions manifest themselves as massless particles. And one type of such massless particles is an axion, okay? Axions have tons of signatures, as we heard earlier. They can mediate new forces. They are very well, they are already, we've looked for them in astrophysics. But the main thing for today is that they are excellent dark matter candidates. Now, when they are dark matter, they change actually the way we think about dark matter. Usually we think about dark matter as a bunch of particles, but because axions generically are very light, it's more convenient to talk about dark matter as a classical field, as a scalar field, whose amplitude is set by the square root of the dark matter density, and it's inversely proportional to the dark matter mass. This classical field oscillates with a characteristic frequency that's set by basically the mass plus the kinetic energy of the particle. And for virialized dark matter, that kinetic energy is very small. So the frequency is basically set by the mass of the field. This field has finite coherence in time. It's only coherent by about 10 to the 6 oscillations. And this has to do again with the fact that dark matter that's trapped in the galaxy is virialized. So, the experiment that I will talk about is crucial to remember that I will be talking about the dark matter as a very classical background, okay? As I said, axions are excellent dark matter candidates because there is a kind of like inevitable production mechanism for them. Now, if you look at the early universe, the evolution of these axions is determined by this type of equation right here, which is very similar to that of a harmonic oscillator. Now, in the early universe, this harmonic oscillator slash axion is overdamped. And the key point is that it's actually very hard for this harmonic oscillator to lie close or exactly at its equilibrium position. Inflation will kick it around. There is no reason to expect that will be exactly at its equilibrium position. So in many ways, when you have a spin zero particle, like an axion in the universe, it's very hard not to have it be at least a subcomponent of the dark matter. As the universe cools, this harmonic oscillator becomes from overdamped, underdamped, and the fields start oscillating. And there you see that it behaves exactly, the energy density stored in it behaves exactly like cold dark matter, which is what we like it to do. Today, the amplitude of the oscillation is very small. So for very light particles, and this small amplitude is what this experiment will be designed to detect. So for axions, the key point of our proposal is that axions are pseudoscalar particles. So axion dark matter produces a time-dependent parity and time-violating background. Okay. Now, in principle, now in piezoelectric materials, which is I would explain what those are, you can have a background that breaks parity. And if you align spins in that material, you also have a time-violating background. So combining these two, axion that is P and T violating itself can produce a P and T even effect, which is in this case a stress or a strain. Now, as I will explain, and as I said before, the most promising coupling for this effect is the coupling of the axion to gluons. Okay. So we'll tell you what this new observable is based on these experiments, and I will tell you how, I will give you a sketch of an experimental setup of how this can be used to detect axion dark matter. So let's start by telling you a bit what piezoelectric materials are. Many of you probably are well familiar with them. These are materials whose unit cell breaks mirror symmetry, and you see it right here. You see this is the unit cell. You see that if I reflect, for example, around the center of the unit cell, this is a breaking of parity, breaks parity. Now, if I stress this unit cell, if I squeeze it, you see that it will create a charge asymmetry across the unit cell. So you will develop an electric field in the material. And whether you, the same thing will happen if I compress it. Now, the direction of the electric field depends on the properties of the material itself. Perhaps the most known material, that the most widely used material, piezoelectric material, is quartz. And you see here there are two phases of quartz. Quartz is made out of silicon and oxygen, and it's like you can think of it as a chain. There are different phases of it in the mirror breaking phase. You can think of the quartz as a chain of tetrahedra, which the center has a silicon atom and the edges you have oxygen atoms. Now, turns out in nature, you have the right-handed phase, I think at 99% level, instead of the left-handed phase. So the ground state of quartz, of silicon oxide, is something that breaks a parity symmetry, and people use this in many applications. Now, in this material, again, as I said, when you apply, so the constitutive equations, I don't even know, can you see the bottom of my screen here?
It depends. Is like you mean in a piezoelectric, and these are like the last two equations?
The equations, can you see the equation at the bottom? Because I have two equations.
We can.
Okay, great. Okay, great. So, so the point is that when you have, so for a piezoelectric material, there are two constitutive equations for the stress and the electric field. Can I go back here? No, I cannot go back. Okay, now I can go back. So the stress, as you know, when you compress material, when you apply a force, there will be a strain of the material, there will be a change in the size of the material. But here, because of you have piezoelectricity, when you compress material, you also develop a dipole moment, an electric dipole moment. That electric dipole moment also results in an electric field, and vice versa. Now, when you have a background axions, and for the QC decoupling that I will be interested in, and imagine that one of the nuclei here has a nuclear spin. For the case of quartz, it would be the silicon nucleus that can have a nuclear spin. These constitutive equations need to be modified to add two types of new tensor, the piezoaxionic tensor and the electroaxionic tensor. One of them, so the electroaxionic tensor, is actually P even and T even. So in principle, it will appear in any sort of material. Any material where you have aligned nuclear spins and you have an axion background will actually be able to produce an electric field across their size. And this is very simple, is because an axion can produce an oscillatory EDM. So when you align a bunch of EDMs, you will produce an electric field. This one turns out is not the most interesting coupling, and I will tell you why. Now, the most interesting probe of the axion is the piezoaxionic tensor. Now, because when you have these aligned spins, now when the axion will actually produce a stress, and this is P and T odd as well. So the axion in this material will produce a stress across it, and that will eventually result in a strain. Okay, and because these materials have excellent mechanical properties, the piezoaxionic tensor is the one that's easier, can be used more easily to probe the axion. Now I need to explain to you how do we start. We need to start from the axion, go to the atom, to the nucleus first of all, then go to the atom and then go to the crystal to explain to you how to actually tell you what the size of this Xi effect is. So the first thing to keep in mind is that if you're in an atom and you have P and T violation, like in the electric dipole moment, there is Schiff's theorem that tells you that the electron cloud will shift around to shield those effects. This is known as Schiff's theorem. This theorem is violated by relativistic effects. It's only true in the electrostatic limit, but it's also violated by the finite size of the nucleus. Okay, so for the nucleus, the first type of P and T odd effects will appear at effectively not at the electric dipole order, but an electric octopole order. And for the nucleus, this is what is called the Schiff moment. Okay. Now for the Schiff moment of the nucleus, the main effect of the axion appears in the interactions between nuclei that involve pion exchange. So in the presence of an axion background that couples to the gluon anomaly, the pion will have an anomalous scalar coupling. And through pion exchange, this will create a non-trivial Schiff moment for nuclei. The size of the Schiff moment grows quadratically with the size of the nucleus for non-deformed nuclei. Now, there are these special nuclei that in most cases, not all though, they are highly radioactive, that they are very asymmetric and they are pear-shaped. Now, in these nuclei, you can have collective excitations of the nucleons, and that gives you an additional enhancement of order of Z in the Schiff moment. Now, once you take the Schiff moment, in order to see what happens to the atom, you will see that naively the electric dipole moment, and due to the Schiff theorem, the electric dipole moment of the atom is proportional to the size of the nucleus over the size of the atom squared. So you would expect it to be very small. You see already though that the Schiff moment gets additional enhancements by the Z and the atomic number of the nucleus. And so something that is naively hopeless may start becoming a bit more not as suppressed. Now, in addition to the intrinsic enhancement of the Schiff moment in large nuclei, there are relativistic enhancements that come in large atoms. So this naive suppression that goes like the size of the atom, the size of the nucleus squared over the size of the atom squared, you need to add additional factors of Z squared, comes from the fact that as the electrons go close to the nucleus, they see the unscreened charge of the nucleus, so the effects of the Schiff moment gets enhanced. So even though you naively started with a huge suppression of this order, the size of the nucleus squared over the size of the atom squared, you find that you can recover most of that suppression. Now, for a free atom, this perturbation actually still gives a zero energy shift when the atom is free. Because when the atom is free, it's in an eigenstate of parity. So if it's in an eigenstate of parity, the energy shift in the ground state appearing due to the Schiff moment only comes in quadratic order. So it's extremely, extremely tiny. Now in piezoelectric material where mirror symmetry is broken, this energy shift can appear to first order in the Schiff moment. And this is crucial for us. And you find that this energy shift is really small, but it still could be measurable, as I will show. And depends on this epsilon s and epsilon p are the amount of quantify for the valence electrons around the atom in the crystal, how much admixture of opposite parity states they have. And this is essentially order 1 for in piezoelectric crystals because mirror symmetry is maximally broken. And I've calculated this 10 to the minus 26 for assuming that we have QCD axion dark matter, okay? Now, so as I said, the way to calculate now the energy shift to go from the atom to the crystal, we need to see how that interaction between the axion and the atom shifts the ground state energy of the crystal. And that you can do in perturbation theory, you just change, you take the derivative of this energy shift as a function of the strain, and this will produce you the piezoaxionic tensor. This tensor is proportional to the shift moment. It's inversely proportional to the volume of the unit cell. And it's proportional to this dimensionless parameter, the derivative of the admixture of opposite parity states as a function of a strain on the unit cell, which we call xi tilde, and this is basically proportional to the, you can extract this actually from the piezoelectric properties of the crystal, and it's a parameter of order 1. So as I said here, this is what we did. So this gives you an idea of what the size of what the size of the of Xi is. Now, how do you measure it? So the first thing you have to do is take a piezoelectric crystal, align the nuclear spins in it using a magnetic field, and then you take 2 electrodes, attach them on both sides, and then if there is an axion background, these crystals will start oscillating, okay? And you can try to use, so if the crystal is oscillating, there's going to be a voltage difference across its plates, and that you can read out electrically, for example, using a squid. This is actually a very well-known technique that people have used for a really long time to detect gravitational waves, and it goes by the name of resonant mass detectors. Back in the 60s, Weber put electrodes across I think it was an aluminum bar, and as the gravitational wave was going through, it would produce a force on the material, and he could pick it out. You could measure the change of the size of the object. Now, today, this technology has been very well developed, and the most sensitive experiment in this game is Auriga, and it has shown sensitivity of a strain to gravitational waves, 1 part in 10 to the 25. Which is extremely sensitive. So it tells you that the technique that we'll be using is actually quite part of the technology that we'll be talking about is actually quite well developed. So, of course, we have to go beyond the Weber bar to detect the QCD axion. So we need to use piezoelectric material, okay? So first of all, piezoelectricity is not something that is very out of the ordinary. Actually, 20 out of 32 crystal symmetry classes exhibit piezoelectricity. Now, the material that we need to use needs to have nuclei with large shift moments and extremely low radioactivity. And there are such elements like samarium. Of course, there is uranium that may be a bit tricky. Neodymium, europium, neptunium. Now, the other thing you want is that material that you use to have very low mechanical losses. and large piezoelectric effects. Okay. So this is an indicative table that shows you that there are candidates material that have, this is their crystals structure symmetry. This is a very similar, very well-known material that people have already used that have similar structure to these quite special material. Now, this is not an exhaustive list. We think people have not, given that this is a new effect, people have not used what is the most ideal material, have not studied what is the best and most ideal material to use for this type of experiment. So a lot of R&D needs to be done to actually identify the best and optimal crystal for this. So the other thing is, there is a little tricky part. Now, because we are excited in mechanical resonance of the crystal, you would naively say, well, mechanical resonance is uniquely set by the size of the crystal. So how do you actually scan the frequency of your experiment? So turns out there are ways to do this. First of all, you can monitor more than one harmonics in the crystal, because a crystal has many acoustic modes. So you can monitor those modes all at once. The other thing is that you can see it, because in piezoelectric material, you can see that they are equivalent, because exactly of their properties, they are equivalent to an electric circuit. So you can actually use external elements, inductor and capacitor elements, to the circuit to actually scan around the mechanical frequency of the crystal. And this is what this plot shows. So one of the big things about using mechanical resonance is that on mechanical resonance, the quality factor of the material can be quite high. In fact, here I show a plot of the quality factor as a function of frequency that we took from our paper. We assumed the maximum quality factor around mechanical resonance of 10 to the 9. I should say, for example, for quartz, it has been demonstrated that this quality factor can be as high as 10 to the 12. Now, as you move away from resonance, this quality factor drops, because now your quality factor is limited by the electrical components of your circuit. So this natural resonance frequency is how we scan by changing. This is the line that we can shift right here by changing the external components of the circuit. Okay. So ultimately, on resonance, we're just limited by thermal noise because the quality factor is so high. But as you start going off resonance, you start becoming limited by the electrical response of your system, basically readout noise from your circuit. So this is basically the expected reach. This is an idealized forecast. I should say that people should take this as indicative, because in reality, we were not really proposing a full-fledged experimental setup. Our idea was, okay, if we assume certain things that we know have been done already, how well can you probe this new Axion observable? So this is the Axion coupling to gluons as a function of the Axion mass. You see the frequency up here. The QCD Axion line is this green line right here. Okay. There are different constraints presented in gray, and I can tell you more later about them. Now, this is in these blue and red bands. You see the sensitivity for different types of setups, where we different size of crystals, different sizes, and we scan electrically around the mechanical resonance. And if you have a setup where you can actually use somehow scan mechanically around the frequency, then you'll have this all yellow thing right here. So the key point to take from this, the takeaway message, is that the piezoaxionic effect can be used to detect, to probe the QCD axion between above frequencies of roughly 10 to the 4 hertz. Now, should you take that this line is here and not there? Well, that will depend when we have an actual setup. Now, one comment is that when people show the coupling of the axion to QCD, when you sit above the QCD axion line, this parameter space is extremely tuned. Okay, so it's tuned because when you couple an axion to QCD, it will get a mass from non-perturbative QCD effects. So all above this line here, the axion is, the parameter space is tuned. At the same time, though, you need to align the vacuum of this axion, the parameter space, so that it doesn't give a huge contribution to theta QCD and spoil the solution to the strong CP problem. Okay. So I actually consider this part of the parameter space completely uninteresting. But of course, in order to reach the QCD axion, you need to go through this parameter space, any experiment that will be looking for it. Now, there are backgrounds coming from magnetic impurities. Turns out this can be controlled. Because we're polarizing nuclear spins in the material, there's going to be fluctuating spins, and those will produce a voltage. Now, this noise, we estimated, it's also small. So we don't there could be other roadblocks, but we do think that backgrounds can be under control. The other interesting thing is that piezoelectric materials that are not spin polarized can be sensitive to other axion couplings, if that axion is the dark matter. The most interesting is the axion coupling to electrons, which is P odd and T even. So this axion will produce a stress across this crystal and will cause it to oscillate. And you can see, if in the future you may be able to go below the white dwarf cooling bound. There are several things to do. What we did in our paper is actually give an order of magnitude estimate of the size of these effects. So we actually need to do concrete calculations to pick the right material for the experiment. The other thing is we also need to optimize the setup. This is, as I said, this is not an experimental proposal. We're just pointing out this new type of observable that we think it's interesting to probe the QCD axion in a range that is currently not being probed at. Now, the QCD, so another thing that we are studying now is the fact that you can use the piezoaxionic effect to actually source axions. So turns out that the piezoaxionic effect can be used to mediate new types of forces between two masses. And this is something that we're currently studying. So to conclude, we believe we have found a new observable for the QCD axion that probes the one coupling of the QCD axion that's model independent. It has the possibility in the future to probe the QCD axion for frequencies above 10 to the 4 hertz of masses around 10 to the minus 10 eV. And it's largely, the important thing is largely complementary to other searches that are currently being pursued. And thank you very much. And with this, I will take your questions.
So thank you so much for this very nice, unexpected talk on a new topic. I think that there will be several questions. So I will start before too many people raise their hands. So perhaps this is a stupid remark, but like if I understand correctly, what you need is to tune and have a resonant effect. You need to tune the bulk modulus, right?
Yes, so you're looking at bulk acoustic modes of the material.
So the easiest way wouldn't be to look. I don't know if there are phononic crystals that are also piezoelectric. Because in that case,
phononic, I mean, phonons, any phonon, we are detecting phonons here, right? So in principle, you can talk to them about that phonons, you can talk to them about them as strain, but in reality,
what I mean is that there are these materials in which you can tune the elasticity, and that's what I was thinking about. So instead of using...
okay. We haven't looked so much into that. Now, there are maybe ways to mechanically tune the frequency, and this is what we show here, the orange. So that's the thing. So the thing that we didn't go too much into it is because we wanted, part of our paper was to stick with stuff that people have worked on. So for resonant mass detectors, people have used this method of applying electrodes and tuning scanning around the mechanical frequency using electrical components of the circuit. So for this first thing, we were not going after to build a full-fledged experimental setup. Our goal was, okay, let's take things that people know how to do. Is this still interesting? This is the question that we wanted to answer. So I think this is a fair point. We haven't looked into it, and I mean, this is part, actually, these things like that are part of what needs to be done. Yeah, thank you.
No, that's like, I understand, like that's a first step, but I was wondering if you already had considered like which kind of
no, it's been hard enough to actually
it's a lot to do. Like, this is amazing. Like, I see the reach. It's more than enough. The final slide is more than enough to justify the work, I would say.
Yeah.
Let's start with the questions from the audience. So there is a question by Martin. Please, you can unmute yourself.
Oh, I cannot hear you.
You are muted, Martin.
Oh no, he's not muted. We just cannot hear him.
No, he's not muted, actually. Yeah, that's true.
No, he wasn't. Yeah, now you're muted.
Can you hear me now?
Yes. Now it works.
Okay,
Perfect.
thank you. Perfect. Yeah, thank you again for this very interesting talk. I just wondering, since, I mean, due to the thermal movement in these crystals, can you estimate, I mean, at what temperature these experiments would have to be conducted in order to supersede the background?
Yeah, good. Yes, good. So you need to go to cryogenic temperatures. You cannot do it at, we're talking about millikelvin order. So this is what we used here. I didn't have time to tell you what parameters went into this plot, but it looks like you need to go to cryogenic temperatures to do this, to suppress thermal noise.
I mean, I think this is the reason why they cannot use radiative elements, because they just...
yes, so this is, we did an estimate. So turns out, so actually, cryogenic fridges are actually, as fridges, they suck. They're very bad at taking out energy to cool a region. So it takes a very long time. So if you have a radioactive element, actually, I forget which one was it. Was it Neptunium? There was one element, I forget now which one, maybe Ken remembers, that was perfect. It had a huge shift moment, but the lifetime was like 10 to the 6 years, not horrible, like something like that. It wasn't. So, but if you take a bunch of materials, the thing would be breaking down. And even for uranium, which is very long-lived, we're talking about lifetime like 1 billion years, it may pose, you may not be able to cool below 100 millikelvin if you use uranium. But I don't think that will be our problem with using uranium. Other people may have other objections about that.
So
thank you.
If there is no further question from the audience, there is Andrea who has a question. Please.
Yeah.
Hi, Mina. Thanks a lot again.
Hey.
So I have a couple of very, very, very short questions. So first of all, when you compute the shift, the shift momentum, you mentioned also the fact that you will need to calculate some interaction potential, I guess, with pions, right? I think you showed that. So typically with pions and nucleon, it's kind of difficult to do computation, right? So I guess that what do you do that? Do you use Scalar perturbation theory or just use some fit from lattice?
So exactly. So a lot of these things have been in the context. So shift moments are crucial for electric dipole moment searches. So there is an entire industry of people that have been trying to do these calculations for decades. Now, as you correctly pointed out, there is still huge uncertainties in the matrix. So in fact, we found literature that in the last 10, 15 years, shift moment calculations have been fluctuating like factors of 10 easily. So, and actually we think, for example, that some of these elements that would be interesting for this type of setup have not really been looked at from that aspect. So, the part that is under control in this full calculation is only the atomic part. So going from the nucleus to the atom, because there they have better methods. But it's true that a lot of work needs to be done to calculate the shift moments.
Okay, thanks. And also related to this, because it was kind of related, you're looking for axion dark matter, and so like an oscillating PT violation, let's say, but what about like static violation? You're not blind to that, right?
Yeah, so we want to think about it. So the problem with static is because it's static. So when you move, when you try to move to measure a static effect, it's like a constant strain, right?
Right.
So you need
I agree, but
it's more difficult to see because you cannot, you don't have a veto. How do you know that?
Yeah, exactly.
No,
so
wait, but if you, it depends, right? If you know what you predict, then you can.
Yeah. So we want to think about it. There are some experiments where people try to do it in gallium arsenide. There's a guy, Hunter, in the US that have tried to do this type of things in solid state systems. Now it just gets, we want to think about it better, but the systematics with it are just at another level. And naively you would say, oh, your signal can be 10 orders of magnitude bigger and you're cool, but in reality the systematics are at a completely different level. So we haven't really spent too much time thinking about it. It would be interesting to think about.
Okay, thanks, Mina. Thanks a lot again for the talk.
Yeah.
Okay, if there